kind of talks on previous Cray architecture, at least 2 of them, okay, some of them, okay, a minority of them, of you, okay. I'm going to talk about a specific architecture, the Cray machine that's in the other room here. CSES hosts multiple Cray MPP machines, and I'm going to focus now on the most recent architecture, which is the Cray XE6. I'm going to start from some years ago when we started the Cray MPP product line, and then I'll show you where this architecture comes from, and then I'll talk about the architecture, about the software, about the configuration, and I'll show you what it takes to run an application on this machine from a user point of view. At the end of this session, you should have an idea of how the machine is built and more or less what happens behind the scenes when you run the application. On another session later today, this afternoon, I'll show you how to actually program, what you need to program an application and run the application on the system. On this part, I'm just focusing on the architecture itself. Let's start with some history. In the second half of the 1980s, we had this old MPP story started. MPP stands for Massively Parallel Processors. And what happened, there were some companies, Thinking Machines, for example, that were starting to build big machines with tens of thousands of processors. We at Cray at that time were running the vector machines, right? Which means low number of processors, but very powerful. And this was a completely different idea. Many, many, many processors, not that powerful. We had Thinking Machines, then we had Intel, Intel Paragon, and then we had some other companies that now are not around anymore. They just built some machines and then fade and then disappeared. At a certain time, Cray decided to jump into this series of machines that were becoming very competitive to our vector architecture. So we launched in 1993 the first Cray MPP machine. It was named the Cray T3D. It was using the most powerful processor, a scalar processor, commodity processor that was available at that time, the DEC Alpha, and it was built with the 3D torus interconnect. And we had a specific version of a microkernel running on the compute nodes. Yes, this was the first machine, and the Unicos Max was the name of the operating system used at that time. One of the interesting features of this machine was that there was a front end that was handling some operating system calls, but the front end was a real vector processor, a very expensive vector processor, just to be the front end of the parallel component. 2 years later, we proposed the T3E, which was using an improved version of the processor. And at this time, the operating system front end was in was one of these DEC Alpha nodes. And there was a different microkernel operating system, Curious-based, which was running on the, let's say, alpha component. And actually, one of these machines was the first supercomputer to achieve 1 teraflop on a real application. Oops. And then MPPs became a common way of programming these high performance systems. And MPI was defined in 1994. I think we had some problems, right? Okay, let's see. Then IBM joined the group in 1995, and then many things happened from them. Then we got Blue Gene in 2004, and then Cray was, in the meantime, Cray had some sad story, was bought by SGI, then he came again around with its own name, and we delivered the first Cray XT3 system in 2004. And this was the first system that CSCS bought from this new Cray company, and it was the first XT3 system in Europe delivered to CSCS in 2005. It's going to be fun, right? Anyhow, the point of this historical digression is just to let you understand that the way we design MPP system is always the same. It's the same today as it was in the early days. So the idea is to find out what we think is the best microprocessor, or maybe the most suitable to what we want to do from the commodity processor available. And then we need to surround this microprocessor with an interconnect that can sustain the performance of the processor and then can provide a bandwidth-rich environment with high bandwidth and low latency as far as possible. Then the third component is the operating system. This is by no means something that can be neglected because it's very important. And we do believe that we can use commodity for the processor. We can't use commodity for the operating system. We need to put some very strong effort on the operating system to avoid interference and to allow the computation to scale up to very large number of cores. Not only the operating system, we need to provide some I/O that can scale, and we need to provide programming and performance tools that can help by programming this very complicated machine. So let's start looking at the XE6. There is a bit of terminology that we need to agree upon, and then I'll show you some slides later on. What is shown here is the XE6 compute node. Okay? The XE6 compute node is built around this, which is the Gemini interconnect. The Gemini interconnect provides two network interface controllers. And so one Gemini interconnect is connected to two nodes. Each of these is a node, and each node is composed by two sockets. Okay? The features of the nodes feature 24 cores. So you have to think of this number, 24. If you want to use the XE6, if you want to run an OpenMP application, a parallel application on the node, you can run up to 24 threads, because this is the number of cores available on the node. There are 12 cores per socket. Okay? So the total number of cores in the node is 24. So you have one copy of the operating system of Linux running on the node and handling the memory space for 24 cores. Okay? The peak performance you can get out of this is the order of 211 gigaflops. That, of course, is a peak performance. Memory depends on how you build the machine. You can have 32 gigabytes per node, or you can have 64 gigabytes per node. The machine that's here has 32 gigabytes per node. And the memory bandwidth, the bandwidth between the memory modules and the processors, the peak bandwidth, it's 83 gigabytes per second. We're not achieving that peak number on any application. We can reach up to 50 gigabytes per core. This is the core, details in the core. So please stop me if I say things that are not clear enough. This is how a node, this is how a node is composed. You have two sockets. You have the cores. This greyhound here identifies a core. So let's say one socket is composed by two dies, okay? And each die has 6 cores. Then there are hypertransport channels that make so that the communication between these cores is transparent, and every core can access memory on every channel. So this is a core, okay? Sorry, this is a die that has 6 cores. 2 dies make up a socket. That's a socket. It's what AMD named the multi-chip module G34. That's a socket, 12 cores. This is what is named Magny-Cours socket. And this is a node. Okay? A node has 24 cores. You may ignore all these things. The only thing you need to understand is that when you run an application which is using only part of the core, you are not using, for example, you can run one MPI task which uses all the 24 cores in the node, and that's okay. But you can do also some more complicated things. You can run 2 MPI tasks per node, which each of them uses 12 threads, 12 OpenMP threads. Okay? So in this case, you want to run an MPI task using these cores and the other MPI task using these cores, because even if a core in this socket can access any memory here, however, the memory is not uniform access memory, it's NUMA memory, which means that for a core in this area, accessing data on this memory board is faster than accessing data on this memory board. So what you want to do is this is named affinity. You want to be sure that, or do as much as you can, to make so that your program accesses memory which is closest, right? Not on the other side of the node, but closest to the die when it's running. And I'll show you how you can do this on the Cray x86.
Sorry. So you were saying that if you assign 2 MPI process to the 2 sockets, you will force affinity.
You have ways to force affinities, yes.
But this is not enough. That's what
yeah, I mean, let's say if you are using all the cores in the node, so if you are using 1 MPI with 24 threads, or 2 MPI with 12 threads, or 4 MPI with 6 threads, things by default go in the right way. Okay? If you are using if you are not using all of them, so if you are using 2 MPI, but each MPI is using only 4 threads, then you need to do things, because what you want to do is 1 MPI here with two threads here and 2 threads here in order to distribute evenly the things. To achieve this goal, you have to do something special. But these are special cases. Okay? Another thing, since we are here, so what happens, for example, if I run 3 MPI, each of them having 8 OpenMP threads? What will happen is that the first MPI has 6 threads on these 6 cores, and then 2 on this other die. The second MPI may have 4 here and 4 here, and the last MPI has 8 here. Okay? So if you do this kind of things, you are using on a single MPI, for example, this one is using cores on 2 different dies and accessing memory on 2 sides of the board. So this is not a nice situation. You should try to use a number of MPI ranks which fits properly in this picture, right? So 3 MPI ranks works, it works, may work slower than you expect due to this fact. Okay? Yes?
Just one question, I'm a bit confused because you are talking about MPI, but I thought that we would use OpenMP because we are on the same node.
Yes. Yes. What I want to say, you've heard Neil talking about hybrid computing, which means MPI plus OpenMP. I'm thinking about an application that runs on 1,000 cores. Okay, so 1,000 nodes, whatever you want. Many of these nodes. Then what you can have, it's a pure MPI application, which means that you run 1 MPI task. You can do this. 1 MPI task on each of these cores. So even if the memory is physically shared and accessible, you can still program in a way as if they were not shared. They were completely distributed. Okay? So you can run 25 MPI ranks on this node. But you can do MPI plus OpenMP, and in some cases this is very useful, especially when you are using a very large number of cores, which means that you are using a number of MPI ranks less than the number of cores here, and each MPI ranks can control multiple cores and use OpenMP to parallelize at the core level. Okay? That's the point of hybrid computing. So, and then I was just discussing what's the best ratio of MPI ranks or MPI tasks versus OpenMP threads if you want to efficiently use all the cores in the node. That's a key point. I mean, we are talking about hybrid computing. Okay? So, if we go a bit down the architecture, try to understand what's behind a single socket. In the processor architecture, in the socket architecture, we have 3 levels of caches. Level 1 cache, we have an instruction level 1 cache and a data level 1 cache. Then we have a level 2 cache, and then we have an extra level 3 cache, which is shared. So each core has a level 1 and level 2 cache, while the level 3 cache is shared by the 6 cores in a die. Okay? So this is a die. That's the terminology. And here are some features of these caches. Should you be very concerned about this? Well, initially not. You rely on the compiler to provide a good code for you, right? But if you want to go down in a specific region of the code and you want to further optimize your application, then you may want to know some details about how the caches are built. How large are the caches? How large is the cache line? So the block of data that are transferred from the cache to the registers, and so on. So you may want to know this level of details if you want to go very far, very deep in optimization. You can find a lot more information about AMD caches architecture in this paper. Let's talk a bit about the interconnect. Okay, as I said before, Cray started again his MPP product line what about 8 years ago. And we did the first machine of this new series was done in collaboration with Sandia Labs, with this Red Storm architecture. And Sandia Labs had developed the interconnect design and the software that should run on this interconnect. So the name of the interconnect of these new XT3 machines, XT4 machine, XT5 machine is named C-Star. So it was built for scalability to reach about 250,000 cores. And this was designed for message passing. So it was meant to support MPI kind of communication. So message passing communication, explicit send and receive communication. With the XC line, which is out for 1 year, maybe, we are designing a different interconnect style called Gemini. And we are designing it in a very different way so that it can provide, one of the reasons we are changing this is that we want to provide hardware support for a different style of communication. So this should be good with MPI and message passing, but should support also what is called PGAS. Which means that sort of implicit communication can happen. One processor can get data from another processor's memory without involving the processor there. So you don't need someone who sends the data if you want to get the data. It's not one sends and the other receives. It's simply one processor addresses the data on the remote memory and gets the data he wants. Okay? And this must be supported by the communication hardware. So we need something in the hardware that can support that. C-Star was not designed for that. Gemini is designed for this. Okay? So we can provide a hardware support for programming languages like the CoArray Fortran or UPC that Neil mentioned before. We are designing yet another interconnect which is called Aries, but that's in the future, and I don't know a lot, and even if I knew, I can't tell you anything about this. Okay, so Gemini, that's the Gemini. As I said before, there are 2 nodes connected because there are 2 NICs, network interfaces. Each interface connects to a node. Okay? The links here built up a 3D torus topology, the same topology we've been using from the T3D days. We're going to change this when moving forward, but this is still the same. So the idea is to scale to over 100,000 network nodes, network routers. And we have designed this to be used for one-sided communication, what I said before, get things from remote memory, which can be implemented also with MPI, or can be implemented with a library named SHMEM, or can be implemented with language structures like the Fortran 2008 with coarrays or UPC. And the Gemini provides also support for global atomics operations. So some reduction or operation like that can be supported by the hardware part. The difference between the C-star topology and the Gemini topology is in the fact that in the C-star we have one node connects, one router, one C-star router connects to a node in the machine, one compute node. The Gemini connects to two nodes. The 3D torus is a simple torus like this. And on the Gemini there are double links, so to speak, in two dimensions and one in the other. And also another communication in the y dimension is built within these two nodes in the hardware in the node itself. I'm showing this because the two machines that are at CSCS are built with these two different interconnect. So Rosa is an XT machine and has the sister interconnect. Palu is an XE6 machine and has Gemini interconnect. Gemini features, there are two things that you need to understand. They are, of course, they are transparent to you. Again, as I said before, if you want to program in a normal way, standard way, you don't need to know these things. If you want to improve the communication, then you need to be aware of some things going on here. There are two mechanisms to transfer data between nodes in Gemini. The first mechanism is called fast memory access. It's what is used by default by most MPI transfer. Supports tens of millions of MPI requests per second, so it's very fast. And you have another way, which is called block transfer engine. This is something that you use if you have very large transfer to happen. And this can run asynchronously from the processor. So you start a block transfer engine operation, and then you can continue your application. You can continue to program, and this goes asynchronously compared to what happens in the CPU. This has some higher startup time, but if your application can support it, if your application and your programming model can support it, it can perform asynchronous communication. Okay, I think the other things are just, well, you can think about 6 gigabytes per second as injection bandwidth, the bandwidth at which you can send or get data out from the interconnect. As I said before, we want to support globally addressable memory with all these languages and libraries and protocols. And this is the major design goal of the Gemini interconnect. How many of you have ever used the coarrays? 0, 1. Okay. It's a Fortran standard now. So if you are a Fortran programmer, you'd better learn this. It's very, very nice. Well, this started in Cray. This started in Cray in the 90s when we had the T3D. One of the Cray programmers thought that MPI was a very stupid way of programming that machine that allowed remote communication, remote memory access. So he designed a set of libraries he called the libgetput. So one processor can get data specifying the address. And this libgetput became the SHMEM library. And then he went one step further. While using a library, I can put this within the programmer, within the language. And so I can apply all the optimization that the compiler can find also to the communication part. And so this now it was called F++, then it became co-array Fortran, and now it's Fortran standard. I don't have example of this, but if you want, just ask me offline and we can discuss about this. Software. As I said, software is the third important component of an MPP system. We now run CLE. CLE is the name of the compiler, of the operating system that runs on the compute node. Cray Linux environment. And you can run it in two ways. You can use in this cluster compatibility mode, which is what you want to do if you have a third-party application that you can change, and you just want to run on this large machine as if they were a cluster. But this is not what we are going to do today. This is not what I suggest you to do. I don't even know whether CSCS has users on this part. What I want you to focus on is this, what is called extreme scalability mode. So the idea is to have a very low noise kernel, lightweight kernel on the compute node that can allow your application to scale without interference from the operating system as much as possible. So the idea is that the nodes in the machine are divided basically in two groups. There are the compute nodes, the red ones here, which are the nodes that you really are using when you run the application, where your Fortran or C or C++ program runs. And then there is a set of other nodes that provide support functions for the application that is running. So these nodes are the nodes, for example, where you log in when you want to compile your application, are nodes, I/O nodes that are connected to the disk or to the disk I/O, to the I/O subsystem, so to speak. So other nodes that provide specialized, let's say, operating system support function. For example, the service nodes, they run a full SUSE Linux operating system. Here is a list of nodes. The boot node is the first node that is booted when the machine is booted completely. This is the first node that boots all the other components. There is an SDB node that hosts a database which contains information for the applications that are running, when they started, the kind of resources they required, and this kind of things. And login nodes, as I said before, the nodes where you log in to when you run, compile, launch the application. And on these login nodes, also the application launcher support is running. This is what you use to decide and to specify, to request that your application is loaded to a particular partition of the compute nodes and then start running on the compute nodes. Another set of nodes are the I/O nodes. So there are some nodes. So you see, for example, the C are the compute nodes. Then there is the interconnect in between. And then you have other nodes, for example, this, where some I/O components are running. So we use a Lustre file system, Lustre parallel file system, and these service nodes run part of the software that is required to provide I/O support for the application. So when your application running on a compute nodes sends issues a writes operation, this means that the data, triggers a communication with the service node running the OST component of Lustre. The data is moved here, and then it's physically written to this by this part of the application, by this service component running on the service node. So software running on the OST does this every 5 minutes. This happens. I don't know what's. Okay. Anyhow, so the I/O part is completely removed from the compute node, and it's delivered by another set of nodes. It's completely transparent. The compute nodes don't care at all about what means to write things to disk.
There's a question that the operation system take care of this. It doesn't mean that you have to
No. Okay.
separate thread which runs on the
No, no, sorry. It's completely transparent to you. You have your program that does the write, and you don't know anything else. Then what happens behind this write is what I've described, but you don't have to do anything on the application level. Okay, so now there is some part of hardware description, how things are built up. This is, in some cases, it's just a curiosity. For other things, this may be a little more important. So the way we build boards, we put 4 nodes on a compute blade. Compute nodes fit on compute blades. And we put 4 nodes on a blade. As I said before, each node has 2 sockets. And each socket has 12 cores. So each node has 24 cores. 24 by 4 is something like 96. So you have 96 cores here. The compute nodes run the Cray Linux environment operating system. It's a reduced version of Linux. On the service node, we run the full Linux. So you have full support for the network component, I/O component, whatever you want. It's a full operating system running there. We can't do this on the compute node, because if we did so, the overhead of the operating system would be too big for the application, and this would affect the scalability of the application. So we need to reduce the operating system part on the compute, running on the compute node. But of course, we still need to provide some operating system support in the compute node itself. And this is a very important component. So for example, if you look at this benchmark, what this does is to count. I mean, this is they run a fixed series of operation on an application, and then see the impact of the operating system, how the running the operating system is affecting the number of operations you can perform. So you see that in some cases, you have a very strong effect of the operating system, and the time it takes to compute this number of operations varies across the time. What happens running the CNL operating system is that this is much more constant and reliable. So you have only in some cases some spikes, but the effect of the operating system on the application is much lower. Okay? And that's basically the idea. So what we've done, we have taken the standard Linux operating system, and then we have put the Penguin on a diet, and we have reduced the number of services running on the compute node, on the operating system running on the compute node. Okay? Software. The software with Gemini. So as I said, maybe also Neil said before, today is a bad day, right? Okay. Okay. Cray MPI is based on MPH2 from Argonne. We are using the CH3 device Nemesis. Maybe it's too detailed for this. There are some components that implement the MPI. We have a low-level interface, which is called UGNI. And then we have a library, which is called DMAP, which is the library that actually implements the data transfer from remote nodes. And this is the library that's called by MPI or is called by the co-array Fortran or UPC to implement the communication. This is completely transparent to you. You are supposed not to use directly this library, so you should not even care about this. As I said before, there is the FMA or BTA transfer modes, transfer components, and you can control somehow, to some extent, you can control whether your MPI communication is using FMA or is using BTE. This is a very complicated picture of the Gemini software stack. I'm not going to describe this. I may want to talk a little about some of them. So you have here That's a user interface to the communication part, and you have libraries here. You can choose to use MPI, which is based on MPICH2. You can use SHMEM libraries, or you can use UPC or CoRA Fortran that rely on this libpguess library. All of them are implemented through the DMAP calls, okay? And ALPS is the launch daemon. It is controlling all these kind of things, and it's talking to the lower component to have the communication to work. Okay. Now I'm going to describe just a little, a few, how the communication happens within the Gemini protocol. You have two ways, basically a couple of ways of communicating. You can use an eager protocol, which means that you have a very small message, and what you do, you put the message in the mailbox, which is the way the daemons communicate, which is the way the Geminis communicate. So you are saving some extra communication bytes or communication effort. It is a simple protocol, but can be applied only where the size of the message is small enough to fit into the mailbox. And then you have standard rendezvous protocol, which is more complicated protocols, but they are necessary to make sure that your communication actually completes. And you can have a get protocol, or you have put protocol. As I said before, Gemini is built with a direct memory transfer in mind. So you can get data from a remote node, or you can put data on a remote node, two ways. It's not basically based on message passing as the other protocol was before, the Portas protocol for the sister. You have a lot of MPICH environment variables that allow you to control things in which protocol you're using, what it means a small message, what's a large message, when your communication fits into this A1, A0, A1, or rendezvous protocol. You can control this if you want. As I said before, this is low-level stuff. It's not the first stuff you have to look at. You have to, but if you have some very specific performance needs, then you have tools to control, to fine control what's going on in your communication library. These MPICH environment variables are described on the MPI man page. And I'm going to describe some of them this afternoon. They are in the paper you have. Then we can decide whether to go one by one or just give a general description, and then you look at them if you are really interested. ALPS. Okay, ALPS is the application level placement schedule. You have an application, you want to run the application on the compute nodes. You need some component that takes your executable, puts the executable on the compute nodes and start the execution, and returns you the output when it's finished. Large part of this is done by ALPS. Okay? The application launcher, the command that you actually need to use is ap-run. You can somehow configure the algorithm that ALPS uses to allocate a partition for you. So for example, if you want to run on 32 nodes, where are these nodes selected from the, I don't know, the 1,000 nodes you have maybe in your XEC system? Something to decide which is the best node that can be given to your application. Several algorithms are available. They algorithms maybe not as possible. Now, or maybe system. access data from the statement, from the programming language level, you can explicitly access data on remote memory. The way you do it in Fortran is using the core array syntax, which now is the standard. The way you do in C is using this UPC extension and Titanium if you really want to do it in Java, but I don't know. I think that UPC is C-based. It's an extension to C. I'm not sure it works completely fine if you are using C++. It doesn't work. Che facciamo?
Te lo ripeti? Era solo la batteria scarica.
Okay. Okay, so yes, what I was talking about is this compute node allocation. There are some ways to some extent this can be configured. The system people are doing this for you. You can do, I don't know at CSCS with CSCS configuration how much you can choose which nodes you want to use, but that depends on the configuration. I don't know, Slarm, for example, how much it allows you to choose nodes here and there in the topology, but
you can choose it if nobody else is using it.
Yes. But in general, you should rely on what the system people have designed for you. Okay, now let's have just an idea of how these things are built. And this is a typical, so to speak, XE6 or maybe XT5 machine. They are about the same. Then you have these things that are called, these are cabinets, right? Within the cabinets, you have three layers of boards, and they are called cages. So you have three set of cages. One cage contains 8 blades. So the blade that I was talking before, with the 4 boards on it, is vertically installed here. So these components here are blades. So you have 8 blades in one cage, and you have 3 cages in a cabinet. Okay. This is a compute blade. Okay, that's nothing serious. Something more important that may affect you, but you shouldn't spend too much time on this, even if it's important to get an idea. It's the topology. You have, I told you before, we have this 3D torus topology, which means a 3D grid which loops at the end of the interconnection. And the way you interconnect, the way you connect, the topology you choose to connect your nodes, it depends on the size of the machine. We have 4 classes of topology. Depending on how many nodes you have, we propose a different way of connecting them. There are many good reasons for this, which may become clear. For example, in this picture, suppose you have, these are cabinets, and these are the cages within the cabinets. If you want to connect these cages together, a naive way of thinking would be to send a cable from here to here and so on, and then you need to close the loop for the torus, so you would need a cable that goes from these 2 cages here. This is not a very smart way of doing, because you have a very different length in the cable, which means a very different latency of the communication. And so the way it's done, it's in this alternate. This connects to this one, and then this goes back like this way. So you have cables which have more or less the same length. So deciding how they are connected, it's the topology matter. You decide how to connect them together. Palu, the XE6 system at CSCS, is 2 cabinet machine. The topology we choose is 1 by 6 by 16. So it's not actually a 3D torus, it's a 2D torus. The first dimension is just 1. This is a so-called XE6M. It's a mini system, so to speak. There are 175 nodes, as I said before, 32 gigabytes per node, 2.1 gigahertz is the clock. That's it. Some of the some of the blades are used for service, for system nodes, okay? And the topology that's configured here, as I said before, is 6 by 16. So you have the Z component connecting blades together. So the blade in one cabinet, and then you move to the other cabinet in this dimension. So there are 8 blades per cabinet, per cage. So this means 16 elements in the Z direction. And the Y dimension goes across the cages, okay? Then you have these extra large machines which have a very different topology. It's 25 by 32 by 24. This is the Jaguar PF machines with 224,000 cores. Okay, now that you more or less have an idea of how the machine is configured, how can you control what's going on with your application? How can you control actually where your application is running, which maybe you can simply ignore this. But if you want to understand where your application is running, I'm showing you which tools you have to use. So for example, if you want to know how your system is composed, how many cores are in your system, how many nodes, what is the clock frequency of your system, in this case you have a very homogeneous system. All the nodes are running at, okay, this is not your system, right? In your case, all the nodes are running at 2.1 gigahertz. This may not be the case. In some other cases, you have a mixed configuration, so you really want to understand what's going on. This command, xtprocadmin-a, provides all the information you want to have about the nodes. So you have a node identification number. You have a node name that reflects the cabinet, blade, and node information. Then for each node, you know whether it's a compute node that you can use for your application or whether it's a service node. How many cores are available in the compute node? What is the size of the memory in the node? And the clock frequency, okay?
And what is the page size?
The page size is the size of TLB page of the memory. It's always 4,000 by default. But you can, we see this afternoon how you can control this. There are some good reasons for doing that. If you use the xtnode stat command, you have this picture. This is a complicated picture for a system which is running, what is 20 cabinets. Maybe this is Rosa, right? So you can see this is a single application running. It's not very meaningful because I'll show you examples of, basically you have a letter that identifies applications. So here we have an application which is named A. This is the letter is chosen to identify the application. And whenever you see an A, it means that the application is running on that node. So you have one application that is running on about all the machine. Okay? There are some blanks here because these are system blades, and a system blade has only two nodes. So you have blanks here. This is a system blade. This is a compute blade, and all four nodes in the blade are used by this A application. I guess this is HPL running on the old machine. Okay, let me try to make this experiment. Okay, this is your machine. This is Palu, and so you can see you can run xtprocadmin on Palu, and you have information about the nodes, node name, and so on. If you want to get the information that I showed before with the megahertz and the memory, you need to run xtprocadmin-a. Of course. You need to be a bit smarter. Okay, what have we done? Okay. Yes, I need to use more characters here. Let's try again. This is the last time. Okay. So you see the extra information about the memory size and the clock speed. As I said before, all the cores here are clocked at 2.1 gigahertz, and you have 32 gigabytes per memory. You see that the service node have only 16 gigabytes per node, 16 gigabytes memory per node, and there are 6 cores nodes. Okay? But what you are really interested in is the compute component, the compute nodes, and they all have 32 gigabytes, 24 cores, and 2.1 gigahertz. Then you can have a look at the machine, and there is nothing running on this machine right now. These are the 2 cabinets of the machine. All of them, all the nodes are available, and you have here the system nodes, and all the other are empty compute nodes. And you have this legend here. If you have a minus sign, it means that the compute node is available. It's free. It's a batch compute node. You could have interactive only nodes, but that's not configured on this machine. All the nodes are accessible by a batch job or by a batch interactive job. I'll show you later. Anyhow, it's considered a batch job. And it's completely empty machine waiting for your application to run. Okay? Sometimes, in a very, very rare occasion, some of these nodes may have some problems. In that case, you see some Y or Z, which means that the node is down, is not available, and you can't use it. Not all of the nodes are available for you. What else? That's it, I think. Then I'll show you later on example of how to run and how to compile and control things. But these are the 2 basic commands. So when you have your application running, you'll see that some of these nodes are actually allocated to your application. Neil, what is the command for the interactive batch?
Samok, 2 L's.
Sure. Dash?
Minus capital N, and then 1, for example, 1 node.
8.
8 node, yeah.
So you see here that my interactive batch job has allocated these nodes here. These have been given to me by ALPS, by the allocation mechanism. These nodes are actually allocated but idle. I'm running this session as an interactive session on these nodes. So now I'm reserving, and I'm running on this node. Now if I run an application that would use these nodes that are marked as allocated, and when the application is running, it will be marked by a code that represents the application. How many of you have already run an application on this machine? Just a few. Okay. Okay. Last part is just, oh yes, but I can't do that. Now, just to give you an idea of what's happening, you want to run an application on the x86. So you log in to the login node, you edit your file, your program, you compile your file, and then you have an executable, and then you are ready to run. Now you use APRun to run the application, and this is what happens when you run the APRun command. Or you submit a batch job is not that different. Anyhow, you submit a batch job. On the login node, there is a batch component that takes care of your submission command. And then, given the number of nodes you want, there is a part of the Alps running on the login nodes that takes care of this and query the SDB database, the SDB node, and gets an idea of what if there are enough nodes available to satisfy your request, and which kind of nodes should be chosen for your application to run. This is not something that you just run AP run, okay? Then someone else, something else is taking care of this. Then what happens on the compute nodes that are chosen by this? So AP run is given a list of compute nodes that it should run on. The first of these nodes is where AP run transfers the executable. So the physical executable is sent to the first of node in your compute partition, and then is distributed by this AP shepherd component to all the other compute nodes. Okay? So at this time, you have chosen the set of nodes your application is going to run on, and your executable has been sent and loaded on all the nodes you're going to use. And then your application can start running on this set of nodes. While the application is running on these nodes, no one else can use your compute nodes. You are the only user on these nodes. Then the application may talk to some I/O nodes and perform some sort of I/O. Okay? Then the job is clean. When the application is finished, these nodes are freed, are returned and marked free in the SDB database so that other applications can use those nodes. Okay, and that's it. So it's clear. You run the AP run command with the application. Someone allocates a partition on the compute nodes you need to use. The application is loaded onto these nodes. These nodes are reserved for your application up to the end. At the end, they are returned to the pool of free nodes in the database, and your application is finished. This is how it works. Okay? I think that's it for this part. And what's next? Do you have any questions? Okay. So if there aren't questions, this means that it's your turn, Neil.
Which pieces of equipment don't work?
I don't know. Maybe it's just this connection. I see there is a pin missing.
Ah, okay.
I don't know whether this has an impact on it or not.
It's fine for me.
Good luck.
And the microphone.
Oh, yes.